Welcome back from winter break. Here we go with sections 5.1 and 5.2 from our textbook. Let's see how this goes. All right. One of the things that we do in calculus, and one of the things that you have to do in a lot of science classes, is you have to find area under a curve. We are going to focus on that particular problem for the entire chapter 5. Right? Now, the problem with finding areas under curves is that curves are curvy.
That's how like my ladies.
Darn those curvy curves. Actually, it's probably a tautology. I mean, the definition of a curve is that it has curves. So anyway, problem with finding areas under the curve is that curves are not straight, whereas most of the area tools that we are familiar with from geometry class are of objects that have straight edges. Triangles, rectangles, trapezoids. The exception being circles, but even curves don't have circular subpieces. They are all different kinds of curvatures. What we're going to do is we're going to explore a way of estimating the area under the curve y is equal to x squared, and over a really small interval, on the interval where x is varying from 0 to 1. And I want to look at a couple different ways that we can estimate the area under that curve on that interval. Are you okay? Yep. All right. So there's the curve. And what I'm going to do is I'm going to start looking at trying to find the area under that curve using rectangular tools only. Now, I think you might be dissatisfied with this process, but we're going to be building toward a much, much bigger idea by the end. Everyone okay? So that curve, and if I wanted to shade it in, I'm just saying, how much area is in that spot? How much area is under the curve down to the x-axis? Anyone want to guess?
7.
7. Well, let me see. This is the point. This is when x is 1. This is x is 0. And this is when y is 1. If I were to look at just this one big rectangle, that one big rectangle would have area 1. I don't think 7 is a good estimate. Yes, Lucy? 0.45. Give me your reasoning, please.
Well, it's just under half.
Because it's just under half. In other words, you look at the space and I say, if I drew this rectangle, this triangle here, that would be half, and this looks like less than half. Okay, Phil.
0.41.
0.41?
Wow.
Are we like, this is like feeling like Price is Right.
He's going with 1 minus the square root of 2.
1 minus the square root of 2.
I mean square root of 2 minus 1.
I would say 0.45, 0.41 are all very reasonable estimates as compared to 7.
I agree.
Okay. So let's attack this problem. Here we go. Oh, look at that. I shaded it in. Yep. All right. I've got an idea. What if I took this curve and I broke it into 4 equal pieces? And what I'm going to do is I'll break it into 4 equal pieces. And again, because I want to use rectangles, because the area of a rectangle is really easy to figure out, I'm going to say, let's take the area of the curve and let's make rectangles out of the area under the curve. And right here is a location. If I break the interval from 0 to 1 down into 4 equal pieces, essentially I'm going to go from 0 to a quarter, from a quarter to 1/2, from 1/2 to 3/4, and then from 3/4 to 1. 4 equal pieces. Each of those rectangles have the same width, and it's 1/4. But what about the height of each of those rectangles? Each of those are changing, and I'm going to use, because I'm arbitrary, I am going to use the height of the curve on the left side, sorry, the right side of that interval to determine the height of the rectangle. Say it?
I said clever.
Clever. Okay? So this point right here, right there, that point is the point 1/4, comma 1/16. How did I get that?
Genius.
Because I plugged 1/4 into the function and I got when x is 1/4, y is 1/16. Okay. What about this point right there? That's the point 1/2, 1/4. How about this point right here? 3/4, comma 9/16. And then this point right here is the point 1, comma 1. Okay, now that I have those coordinates, I'm going to say, well, let me just add up the areas of each of those little rectangles, and the sum of those areas is an estimate of the area under the curve. We'll debate later, good or bad. It is an estimate. Well, I'll go with the largest and easiest rectangle first. What is the area of this rectangle right here? It's 1/4 wide and it's 1 tall. It's 1/4. What about this rectangle right here? It's 1/4 wide and it's 9/16 tall. 9/64. How did I get that again? This, because this distance here is 1, and I broke it into 4 equal pieces. So this rectangle is 1/4 wide, it's 9/16 tall, and 9/16 times 1/4 is 9/64. Double and double again. Okay? How about this rectangle here? It's 1/4 wide and it's 1/4 tall, 1/16. And then this little rectangle right there. Can't even write the answer in, it's so small. It's 1/4 wide and it's 1/16 tall, 1/64. And I declare that 1/64 plus 1/16 plus 9/64 plus 1/4 is a reasonable estimate of the area under that curve. I would love to know what that sum is. 15 over 32? 15 over 32. Okay, by the way, I am going to give this answer a special name as well. Now this is going to be based on our new textbook. You'll see things later in the slide based on the old textbook. But they call this RAM 4. Well, I think the easy part is the 4. I use 4 rectangles.
The R.
One of the R is standing for rectangle.
And something.
Okay, and I base the heights on the rectangle based on the right-hand side. This is the right rectangular estimation method. Approximation. Estimation, approximation. Yes?
Would it be more accurate to use 1 and 4?
You have a great thought. We're going to get there in a little bit. Right, meaning that the heights are based on the right-hand side. Rectangular, I'm using rectangles to fill up the space. Approximation method. And the 4 because I use 4 rectangles. Lucy, you're absolutely right. And we're going to go and I'll show you some other stuff in a little bit.
Call it right-hand estimate.
Did we do this?
We can call it the right-hand estimate. In fact, on the AP exam, they're going to call it the right-hand estimate. Did we what?
Did you do this in stats?
Pretty sure.
It has nothing.
Well, no, there's area under curves and stats as well. But, no, I don't. Oh, wait, we did do something area under the curve for continuous probability functions.
Exactly, yes.
Sorry, Lucy and I just operate at a higher plane than you do.
That's doing inside jokes, and I don't like it.
We operate on L3.
All right. So, there's our estimate. Our RAM, our right rectangular approximation method, or as Tyler called it from, because you were in AB last, right?
Yeah.
Okay, you call it the right-hand estimate. All right. And here's me doing the same work. 64th, 16th, 9/64ths, 1/4, 15/76. Everything's cool. We did everything the same.
Oh my god, Lucy, you were so close.
It's an estimate. She was close.
But it's an estimate.
The answer.
I know.
Ready? Now, besides the RRAM, there's also the LRAM. All right? Or, as Tyler would call it from last year, the left-hand estimate.
If you take the average of both, will you get the answer?
Because it uses the right hand.
Well, like, you guys know the answer, so we know.
We'll get there. We're going to get there. All right.
Tell me average.
So what I would like to do, I'd like to do this problem again, but let's use the left-hand estimator. Now, what do we mean again? We mean that we're going to describe the height of the rectangles based on the height of the function on the left-hand side of the interval. So again, we were in this interval here from 0 to 1/4, and then from 1/4 to 1/2, from 1/2 to 3/4, and then from 3/4 to 1. Let's use the biggest rectangle first because it's kind of easier to see. Didn't we know what the value of that function was there? Wasn't it 9/64? This is 3/4, 9/64. So the area of this particular rectangle, it's 1/4 wide. That's not 9/64.
9/64. It's
9/16.
No, that's the.
It can't be 9/16 because that's more than half of the big one.
That's what we were.
That's the
Okay.
area.
I think I know where the problem is.
Oh.
This coordinate is 9/16. The area of this rectangle is 9/16 times 1/4, which is 9/64.
Yep.
And in fact, this rectangle, we've already calculated before,
It is the 1/16.
1/16.
This
This one here,
is the 1/64.
1/64.
The other one's
And this one here, that rectangle right there,
128.
is 0.
So it's the last.
You're close.
Well, let's go through that one more time. What's the width of this rectangle? 1/4. How tall is that rectangle if we're using this point right here to estimate its height? 0, because the function type is 0 at when x is 0. All right? So, if we add up 0 and 1/64 and 1/16 and 9/64. Okay, let's go. Boom, 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 boom. 7/32 is correct, Caitlin. Way to go. We're starting off 2011 really well. And again, your book is going to refer to this as LRAM 4. The left-hand estimate using rectangles, and we use 4 rectangles to do it. And that ends up being a little over 20 hundredths. So far, so good? So that's LRAM, RRAM, one more. Middle RAM.
Yeah.
And the answer is midpoint. Now in the midpoint estimator, again, we're still breaking up this into 4 equal parts, but the height of the rectangles is going to be determined by the midpoint of the interval. So let's take a look at this last one for example. 3/4 and 1 are the boundaries on that interval. What is the middle value on that x interval? 7/8. Are we all in agreement there?
Yeah.
Which means the coordinates of this particular point is 7/8, comma 49/64.
Wait, how are you getting the y value?
Because this curve is y is equal to x squared.
Oh, never mind.
So I'm taking the x value and plugging it into that. We kind of lost that because it was way back on like the second slide. Okay. Can we please come up with a coordinate for that particular point? 5/8 is the x value. And 25/64 is the y value. How about this point? 3/8? And 9/64. I can hardly write that small.
Write it huge.
I see, wait, what's the?
If I'm between 1/4 and 1/2, which is like being between 2/8 and 4/8, the middle point is 3/8. 9/64. And then lastly, the point right there. Okay, no, that's the the x coordinate, and 1/64.
Sorry. What is it?
This is called the MRAM, or the midpoint
They're all
estimator.
perfect squares, the y value.
What's that?
Numerator and the numerator and the y value, they're all perfect squares.
Awesome.
In fact, they're all the same perfect square.
Yeah.
So this problem, adding up all these areas, should be a little bit easier. This first rectangle has a width of 1/4 and a height of 1/64, and it has 256ths in its area. We agreed? This next rectangle, it's 1/4 wide and 9/64 tall. And its area in the second rectangle is 9/256.
Like that number.
Yep. In the next rectangle, it's 1/4 wide. It's 25/64 tall for a total area of 25/256. And then the fourth rectangle, again, it's 1/4 wide and 49/64 tall for an area of 49/256. MRAM 4. Again, this is the old notation, the new notation in our book. MRAM 4 is going to be the sum of those numbers 21/64 when we reduce the fraction, or 30.328125. How are we doing?
Pretty good.
Pretty good?
Just around.
Making sense, right? All right. Now, I have a question for you. I would say at this point, I'd say the area is somewhere between 0.21875 and 0.46875. And probably the best estimator out of those three is the midpoint.
You're wrong.
I'm wrong?
Yes.
Okay. Why am I wrong, Phil?
Because it's not. There's extra box that covers above the curve.
Okay, I'm going to put this in.
Yes.
You can average them.
I can average them?
Hopefully.
Can we do
That was my
Yes,
guess.
we can.
Yes, we can. All right. Okay, let's talk a little bit about overestimation and underestimation for just a second. The one that was 0.46, I would call that an overestimation. Would you as well?
Yes.
Why? Because there's extra of the rectangle on every single one of them. Was extra box. Okay, I'm going to write something that's a little bit more general. When f is increasing, RAM overestimates. And it's kind of like what happened just now. Every time I use the right-hand side to determine the height of the rectangle, there's always this little extra area. So when f is an increasing function, the RAM overestimates the area under the curve. LRAM underestimates.
And middle round stays the same.
Okay, and I'm not going to make a comment about MRAM,
No one can.
whether it overestimates. There'll be another time for us to look at that. By the way, that's what we saw in this particular example. Guess what? When f is decreasing, it switches. RAM underestimates, and LRAM overestimates. Now, why is that so? Well, let me draw a picture of a decreasing function. If I draw the RAM, if I draw all the rectangles associated with the right-hand estimate, so here's an interval, here's an interval, here's an interval. Always using the right-hand side to draw the height of those rectangles. You'll see that there's a space in between the top of the rectangles and the top of the curve. No, go ahead. If I draw the same curve and I draw the LRAM, again, let's do it with 3 estimators. And I use the left-hand side to determine the height of the rectangles. You'll see that there's always a little bit extra above. So when the function is decreasing, RAM underestimates and LRAM overestimates. Are you okay with that idea?
Yeah.
You love it?
We married that.
Okay, great. Now let's get back. Let's get back to an idea that Lucy had. And that is, what if we use more rectangles? Now, the reason why I use 4 rectangles for this particular example, because it's kind of easy to do the math. You know, we calculated the area of 4 rectangles, added them up. You don't want to do that with 10, do you?
No.
Would you get a better estimate?
You'll get a better estimate, but you don't want to do it by hand, do you? I happen to have a calculator program that not only draws the little rectangles, but then estimates the area. can you please tell me what kind of estimate this is?
It's a right-hand estimate.
It's a right-hand estimate. It's an LRAM. Sorry, right-hand. It's an RRAM. And what happens? When I increase the number of rectangles to 10, so this is an RRAM 10, the sum of the areas of those rectangles ended up being 0.385. Now, believe me, that's still an overestimate. It's still an increasing function. 0.385 is still too much, but it's closer to the real answer.
Can't we just like do what you said? Just keep doing right hand and left hand.
Well, tell me, what are we looking at there, Paul?
Left hand.
That's a left-hand estimate. That's an LRAM. An LRAM. LRAM 10. Can you see the n equal 10?
Yeah. Do we have those?
The one on the left.
Not yet.
Somewhere.
Are you gonna go?
Yes.
Okay.
In fact, I wish I had it ready for you right now, but I don't.
Okay.
All right? Anyway, LRAM 10. 0.285. That's a better estimate, but it's still an
Underestimate.
underestimate. Is that an MRAM?
Yeah.
Does it look like
No, that's a. Wait, you say hammer?
M?
Oh, okay.
M.
Yeah. Yeah.
So this is MRAM, this last one.
Yeah.
The height of each rectangle is determined by looking at the height of the curve in the middle of each interval. And that one ends up being 0.3325. And we don't know about its estimate.
Wasn't it
I didn't make any statements about whether that's an overestimate or underestimate.
still be a little over because it's an increasing function? So like,
I'm not going to make a comment.
okay.
All right, and that's the best we can do. 10 subintervals. That's the best we can do. A million. That's crazy talk. Okay. Well, actually, what I have here is 20. Can I just keep going? Well, we're going to go for that thought right now. Okay, when I went to 20, what did I end up getting? Again, end up getting a better estimate than either 4 or 10. The RRAM still overestimates for this increasing function. The LRAM still underestimates for this increasing function. And perhaps our best estimate of all is the midpoint at 0.33125. Again, as Billy had mentioned, why do we have to stop there? We don't. Okay, it just keeps going. Okay, put down your pencils, because I don't want you to write down what's on the screen next. I don't even want you to be tempted to write down what's on the screen next. You ready?
Is it chocolate?
Caitlin's like, not a problem.
Throw themselves over.
All right,
Oh.
don't worry about this yet. You're not tempted to write this down. Okay?
It's very untempting.
Very untempting. This is another way of looking at what's called looking at RRAM. I don't know if you can discern what this means. 1 over n on this particular problem. It's the number. N is the number of rectangles. So 1 over n is the width of each individual rectangle. Okay? This expression, right, if this is the width,
That's the one.
this is the height. Okay, when I is equal to 1, this is the expression 1 over n. Let's say if n was 10, this is 1/10, 1/10 squared. Oh, that would be the height of the first rectangle using the right hand. When I turns into 2, as this notation would have it do, this becomes 2/10 squared, 3/10 squared, all the way up to when I is equal to n, or 10, 10/10 squared. That gets us that far. So this is another way of looking. This is another way of looking at adding up all of the small individual areas and getting an estimate. if you were curious, the difference between RRAM and LRAM. Oh, I'm sorry. Don't write that down.
That's so much
Clear
clearer
now,
now.
Mr. Fadoir.
Here's what I want you to get out of that. Okay? If I clean this up, at this point there's a jump where I can lose the sigma notation. You may have learned, or you should have learned in pre-calculus, although I am not going to hold you to this, that sigma of I squared as I goes from 1 to n is equal to n times n plus 1 times n plus
Yes, of course.
2n plus 1 over 6. You may have learned that. But let's just say I can make that jump, I lose the sigma notation, and I get this expression. So know what that expression does? If I know the value of n, I can plug it in there, and out I get the estimator. So if I say, if I want RRAM 4, I put 4 here, 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 and there, and out comes the estimator with 4 rectangles. If I want RRAM 10, I can put 10 in those 4 locations, or 20. So I can do this for RRAM and LRAM, because here's LRAM. And here's MRAM. Nope, I don't want you to write any of them down. What I want you to see, though, here's what I want you to leave this here with, that we could write expressions that for any value n you give me, I can give you back the estimate based on that number of rectangles. I don't have to calculate them individually. Now, in the exercises that you're going to do for homework, you're going to do them individually, because you don't have the skills to do this part yet.
Oh, really?
Yeah.
Really?
Challenge you to a sigma notation off.
Funny.
Probably gonna lose, but
All right. And by the way, since I now have the ability to just, you give me a number of rectangles, I can just plug it into an expression. Here's what happens with 10 subintervals, 20, 30, 50, 100, 1,000. Would you please remember for this increasing function that RRAM always overestimates? For this increasing function that LRAM always underestimates? And we didn't make a conjecture about MRAM. But what do you think's going on? Stephen?
I think that MRAM is determined by the derivative rather than the function itself. Whether the derivative is increasing or decreasing.
Okay. And the answer is well, no, there's a fourth way of estimating called TRAM, and TRAM uses what Stephen just said. It uses how is the slope changing. It uses essentially the second derivative, but we're not there yet. So what?
we're using zero for the derivative.
All right. So, does anyone have an estimate now about how much area is under that curve on that interval? About a third? Yeah?
I'm gonna say
0.31? I think that LRAM underestimates, and this underestimate is bigger than 0.31. So I think 0.31 can't be the answer.
Oh, let's just wait.
Okay.
I think it's between LRAM and.
Oh, I'm sure will.
I think so too, because since both of them create boundaries, it's some number in between these two numbers. I agree.
No,
Danielle.
between LRAM and MRAM.
Oh, okay.
I think that it might be MRAM would be the best estimate because it's over and underestimated. at the
It seems
same
to
time.
balance
Like
itself
the
out.
rectangles, it balances itself out, and it seems like a happy medium.
But it seems like it kind of overestimates.
I think that's the great viewpoint. Ready? Here's my last point. Well, not my last point. I'm going to say something facetious, and then you're going to.
Wonder what.
You don't know what facetious is?
I think you just the answer. What did I say?
I said I was going to say something facetious, and then you're going to correct me on it. Ready? And 1,000 is the most number of rectangles we can do.
Yes.
No.
Infinite.
It's infinite.
Infinite. How can we talk about having an infinite number of rectangles?
I don't know.
I don't know.
Oh.
Should we write this?
Yes, you should write this. Something interesting happens as you go from 10 to 20 to 50 to 100 to 1,000 rectangles. If you go on, and as n approaches infinity, we no longer get estimators to the area under the curve. I'm going to say that one more time. As n approaches infinity, we no longer get estimators for the area under the curve. What we get is the area under the curve. The area under the curve is the LRAM and the MRAM and the LRAM with an infinite number of rectangles. The error, meaning the amount of rectangle that is above or below the curve, essentially goes to 0 as the number of rectangles goes to infinity. This is a very, very big idea. Got the big idea?
No.
So
No.
it's the number of rectangles goes to infinity.
LRAM is no longer an estimate. LRAM is the area.
So as they get closer to like an
So they're
infinite amount
I
of
say what, as they get closer to infinity, the estimate gets better and better. The limit as n goes to infinity is the area.
So you could do L or R, doesn't matter.
And it won't matter which one you do. Now, writing a calculator program that will add up those infinite number of rectangles will take an infinite amount of time. All right?
So it's like
It's a good thing, though, that we've got other tools to work with, other than calculator programs then.
It is a good thing.
It is a good thing. Tell me when I can go on to the next slide, please. Let's see Charlie's still writing. You take your time.
Oh, I'm fine enough.
You're fine? Everyone else fine? All right.
I
I want to go here, for example. There's MRAM. There's an expression that if you tell me a number of rectangles, I can plug it into those places where the ends are, and I would get the estimate based on that number of rectangles. But we had said the area is equal to the limit as n approaches infinity of 4n cubed minus n over 12n squared. Or cubed, sorry, cubed. Can we figure out what the value of that limit is as n approaches infinity?
Yeah.
What did we learn way back in chapter 2? As n goes to infinity, what doesn't matter? That n. As n goes to infinity, this n cubed and n cubed,
Just equals
these two n cubes, when n gets really big, this minus n doesn't matter. And essentially you have 4n cubed over n 12n cubed. And what did you say, Phil?
1/3.
This is just 1/3.
Should we write
Just go with this for a second. So when I use MRAM with an infinite number of rectangles, I say that the area is 1/3. What do I want? Slide 14. Hey, here's LRAM. What happens when we have an infinite number of rectangles for this? Okay, let me clean this up. Let me clean this up just a little bit for you. Ready? This times this is going to give me an 2n squared. Right? FOIL method.
Yeah.
And a bunch of other things.
It won't matter.
That won't matter. I'm going to end up with a 2n squared on top and a bunch of stuff that doesn't matter, divided by 6n squared on the bottom. What happens when I go to infinity there? Oh, I go to 1/3. Oh, where am I?
Slide 41.
Okay, and here's our RAM. Do the same thing in your head. What's going on with our RAM as n goes to infinity? I end up on top with something that's 2n cubed, and a bunch of stuff that doesn't matter. On the bottom I have 6n cubed. And it ends up being 1/3 as well. So, my interesting point, see if I can find that slide again. There it is, the interesting fact. It does not seem to matter whether we make our estimate the right hand, the left hand, as long as we have an infinite number of rectangles. When we can't do an infinite number of rectangles, then we can look at characteristics of the curve to figure out which one gives us the best estimation. Have I lost anyone yet? Not yet. Something bad going to happen next? I hope not.
It's a new area of science.
That was page 41, page 18. So.
Okay. So, here's what the book, at least my old book, used to describe area under the curve then. Since it does not matter if you have an infinite number of rectangles, why not use the right-hand estimate? If you want to find the area under the curve, and you're going to use an infinite number of rectangles, you could just as well say, I'm going to use the limit as n approaches infinity of the right-hand estimate. Or, you could say this. X sub I star. Now let me tell you a little bit about what X sub I star is. First of all, I had used this idea of I on my sigma notation. When I goes from 1 to n, it starts at 1, then goes to 2, then goes to 3, and goes to the 4. It goes through all integer values starting at 1 and ending at n. Alright? X sub I then is something having to do with an x value in the ith interval. Where if I was 1, we'd be in the first interval. If I was 2, we're in the second interval. Okay? X sub I star basically says it doesn't matter which value you choose in the ith interval. Because what happens, as the number of rectangles increases, the width of every rectangle decreases, and you end up squeezing to a single value anyway. So they use this notation. Any value in the ith interval will do. By the way, this, what we just did, has a special name, and it's called, oops, Riemann Sum. Bernard Riemann, mathematician, 17th century. Swiss, I think. Austria, if you guess German, Austrian, Swiss, French, you probably will be right for everyone except Newton.
Maybe not the French.
Newton was German.
Newton was British. English. Newton was very, very English.
He talked like that. Sorry, it's my great accent there.
That was a terrible version accent.
Paul, let's hear it again.
Sorry.
Let's hear it again, Paul.
No.
Okay, let's switch gears. I want to actually talk a little bit now about why we're interested in areas under the curve. Right? Story problems, sure. Okay, so can I talk about me driving for 3 hours at a constant speed of 70 miles per hour? You're like, this is easy.
Residential.
210 miles, easy peasy, right?
You gotta be
What's the
going.
area under the curve?
Nothing but my hairy wrists. You're like, that's more detail than I really need. All right. What I want to do is that you already know the answer to this question. It's 210 miles an hour. You already know that. My point is, can I look at this situation graphically for just a moment? If I think about the graph of time being on the x-axis and speed being on the y-axis, I could think of the area under the curve as representing something. The area under that curve is indeed the distance traveled. Areas under curves actually are meaningful. Where have you done this? In science class?
Physics.
Okay, so tell me about the physics experiment or the...
It was like a velocity versus time graph, and then
The area
Yeah,
finds this
just-
placeholder.
right, so you just found like triangles and rectangle area to find displacement.
Okay, and that's exactly what we're building towards. In this particular situation, the rectangular area is really easy to find, is it not? It's 70 tall, it's 3 wide. The area under that curve is 210 miles. The area under this curve is 70 miles per hour multiplied by 3 hours. The area under this curve is 210 miles. Now that one's easy. What we need these techniques, the LRAM, the RRAM, the MRAM techniques for, is what happens when the velocity is not constant. When the velocity is nice and constant, 70 miles an hour, it's an easy problem. You can do it without doing anything graphical. But when the velocity is varying, you find that amusing, Patrick.
I don't know if anybody else is watching.
Over the holidays, we played Just Dance on the Wii. We walked like an Egyptian.
I clicked the next.
That's cool.
I heard that's a really cool system. Okay, so here we go. Let's do a problem. Let's find the area under the curve to find distance traveled, but this time with data. So this could be the acceleration of a car. Not a very fast car because it takes 6 seconds to get up to 60 miles an hour.
It's not a Lamborghini Murcielago, but it's like a 2003 Subaru Elite.
Or the 2004 Saturn Vue that I drive. With the big 2.2 liter engine. 0 to 60 in minutes. All right, so I've got a problem. I've got this data. I'm standing still at time 0. By the end of 6 seconds, I'm going 60 miles an hour. I want to know how far have I traveled in those 6 seconds. Now the answer to this is it's the area under the curve. Now there's a problem here, and I want to see if anyone notices what the problem is with this data.
It's not a
not constant.
Well, we don't know the equation. It's not constant velocity, so it's harder than do the other problem. Charlie?
Well, it's average, so it's not like
It's average.
your speed.
No. At the instant at 1 second, I'm going 16 miles an hour. At the instant at 2 seconds, I'm going 30 miles an hour.
Yeah, but
It's-
whatever happened in between those, like, you know.
Well, we don't know.
It's not constant.
Hit a bear.
It's not constant acceleration. True. Because as we time between 4 and 6 seconds, I only gain 6 miles an hour. Whereas
Low.
my acceleration is like 16 miles. No, I don't know what my acceleration is there. I got a problem here with units.
Miles per
Miles per hour,
second.
but it's
I got miles per hour for 1 unit,
Oh,
oh, you
that
can.
one was kind of.
and I got seconds for my unit of time. Tell you what, here we go. I'm going to redo this. There we go. I'm going to change my speeds so you don't have to. I've now converted all my miles per hour to feet per second. Feet per second? Did you say?
I don't know. We should do feet per minute though, just to mess everything up. I think that'd be fun.
Yeah, fun.
Yeah. It sounds great.
It does.
I don't think feet per second's that accurate.
No,
Version.
on the conversion, I did some rounding, just to make our lives a little bit easier. So let's say this is our new data. I start at 0 feet per second, and by the end of 6 seconds, I'm going 88 feet per second. I would like you to estimate how far I traveled. Let's use the right-hand estimation first. How would I do that?
Get your rectangles going.
Get my rectangles going. So how many intervals am I going to use? 1, 2, 3, 4, 5, 6. There are 6 intervals. The first one's going from 0 to 1.
First one was 7.
The second one's going from 1 to 2. So I could say that our RAM 6 is equal to, and what does that first rectangle look like? How wide is it? 1/6. No, it is not 1/6. It's 1 because I took 6 seconds and broke it up into 6 equal parts. Each part is 1 wide. 1 wide and how tall? 23 tall. And there's my first rectangle. How about my second rectangle?
Just add the speed.
2 times 44.
Not 2 times 44.
I meant 1 times 44.
This width is 1 between all of these. 1 times 44. And what about the next rectangle? 1 times 62. And what about the next rectangle? What is it? 1 times 76? And then the next rectangle after that? 1 times 85. And the next rectangle after that? 1 times 88. Now someone said just add up the speeds. In this case, that indeed would work. But it doesn't work every time, and so therefore I want to be cautious about that. What do we end up with? 378. 378. You are so far incorrect. What? Fits. Fits. Okay. Yeah. So these problems, be careful, we're going to have units. Last thing, on this particular version of the problem. Did I really go 376 feet? Why not?
It's an estimate.
Because this is an increasing function, so this particular approximation method overestimates the area under the curve. Yeah, Lucy?
What is the S of that?
I don't know. You guys said fits, and so I wrote it down.
Second.
No, it's not feet per second.
It's just feet.
It's just feet. The area under the curve is going to be. No.
It's not an area, it's distance.
Okay, because. Okay, hold on. Let's just look at this first rectangle. How wide is it? No, it is 1 second wide. How tall is it? 23 what? Feet per second. The area in that rectangle is 23 feet. Yeah, I know. All right. So 378 is an estimate. It's a reasonable estimate, but it's an overestimate. Come on, try it one more time. There we go. LRAM 6.
I'm gonna take a guess. It's 290.
Okay. We're going to go through it. We're going to go through it. Okay, first rectangle is 0. 1 times 1 wide, 0 tall. Plus 1 times 23, because this rectangle here is 1 wide and 23 tall. How about the next rectangle? One times 44. Oh boy, am I off. Try that again. That is horrible. Where did I go wrong? Right.
Put another line on the next one going down.
Oh, I
Just
see.
keep drawing the line straight down from the point, and then.
There you go.
Is that better? Okay. And by the way, if you see the trend, the next rectangle is 1 times 62 plus 1 times 76 plus 1 times 85. So in other words, if you took this old value, got rid of the 88, and added a 0, you end up with.
I wonder what Genie's done there.
All right. Hey, 290 feet. That is a reasonable estimate, but it's an underestimate about the area, the distance traveled by that car at that time.
You need a okay distance. Like a meaning in between, yeah.
Right? A third-party estimate. Okay. I'm going to write something. You're going to tell me it's wrong, and then I'm going to tell you why it's right.
Or it's wrong.
The last one we're going to do is MRAM.
Three.
By 3.
That's wrong.
That's wrong.
Right.
No, I like it. I think it's right.
Leave it that way.
It would just be passing
Because
through
we
the
don't
points at
have
1,
because we
3.
don't have
Why
the
is it
midpoints
right?
between
Because we
those.
don't have a function here. I don't know how fast it was going at a half second. I don't have a midpoint because I don't know the function. So what I have to do is if I want a midpoint, I've got to create intervals where I actually have data, where the midpoint has actually got a data for me. And so what we end up having is this interval, and that interval. Those are my 3 intervals that I actually know the midpoint function value. If I was going to draw this in rectangles, it would look like this. Now, the problem here is before with midpoints, we said, they give the best estimate. But now we've just thrown away half the data. No, we've thrown away 4/7 of the data. We're only using 3 out of the 7 data points.
Correct.
So it's like, is this a better estimate?
Yes. Whatever.
What's prior?
Okay, let's find out. What's MRAM 3? Well, what's the width of the first rectangle? 2. What's the height of the first rectangle? 23. Second rectangle, what's its width? 2. What's its height? 62. Third rectangle, what's its width? 2. What's its height? 85. And someone with a calculator, give me a total. 340.
I heard she good at them software.
All right. And actually 340 is probably the best estimate. We know based on the LRAM that the LRAM is an underestimate. We know that the RRAM is an overestimate. This number is in the middle. No, really, 340 is between 290 and 378. It really is. Oh my God, yeah, I did put these. All right. So based on data, we can also do these estimates. You okay? You good with that? All right. All right.
Would they want us? Is this the end of the problem?
Yeah.
Okay.
I mean, typically these problems, they give you data and they ask you to do something with this data. One of the things you do with data is you answer the question, and they often come back with, does this overestimate or underestimate the true value? We believe that RRAM overestimates, right?
So if it just asks you for like the distance traveled, do we have to do the RRAM, the LRAM, and the MRAM, or can we just cut to the?
Okay, on my test, on the AP exam, they will tell you which estimation method they want you to use. Tyler, can you confirm that from your remembrances of the AP exam last year?
I didn't take it.
Okay. My remembrances from looking at all the free response questions that I had access to is if they give you information like this, and they want you to estimate, they'll tell you which estimation method to use.
They will tell you that.
Yeah.
I remember.
All right.
You had to practice. No.
All right. And by the way, this is just me doing the problems that we just did. 378, 290, 340. Does it all match what we did?
Yeah.
All right. T. T. Let's not do that.
That's scary.
Trapezoid.
Oh, that's really
Bored.
Wait, which? I just want to see it. I want to
Okay. Trapezoid. Now, let me tell you about trapezoids.
Why do they matter?
Why do they matter? Well, first of all, I'm going to say something about what you think trapezoids look like. All right?
You're going to tell us.
No, because most of you are already...
No.
Is that a trapezoid? Why? But no, one person at a time. I want someone to just totally nail this. Why is that a trapezoid? Well, I'll go with Charlie.
It has one pair of parallel bases and 4 sides.
Okay, it's quadrilateral, because it's 4 sides, and it's got at least one pair of parallel sides. Tyler, is that what you were going to say?
Yeah.
Steven, is that what you were going to say? All right.
And another pair that is congruent.
Are they congruent?
They don't have to.
They don't have to be.
Yeah.
There is no guarantee of congruence in a trapezoid.
Then how would it be parallel?
The other
If that's not the other two,
They can be different lengths.
Wait, hold on. So if I draw this, that's a trapezoid,
Oh, snap. Yeah,
right? Are there any congruent sides in here? None. Okay. Is this a trapezoid?
Yes.
No.
Yes.
One person, please. I want someone to take take the affirmative. Yes, it is. Someone to take the negative. No, it isn't. Hannah, is this a trapezoid?
No, because it has more than one parallel side.
Okay. And here's the problem. Ready? That definition doesn't work. Sorry. No. Sorry. That definition is needlessly restrictive.
Okay.
The definition of trapezoid that should have been taught in geometry is that a trapezoid has at least one pair of parallel sides.
Right. Okay. Yeah.
So if it has two pairs,
It still is.
it's still a trapezoid.
Wait, that's a rectangle.
A rectangle is a trapezoid.
All rectangles are trapezoids, but not all trapezoids.
Boom!
But a
Squares.
rectangle.
Did you hear her? All rectangles are trapezoids. All squares are trapezoids. Just like, just remember, you remember that moment where someone told you that rectangles or squares are rectangles?
Yeah.
And you
But
had
not all
to, and you had, all squares are rectangles. You had to move beyond that point, didn't you?
By saying that
And
all cardinals are birds, but not all birds are
exactly. So at one point in your mathematics education, you discovered that fact that all squares are rectangles, and that this notion that the sides have to be unequal for it to be a rectangle goes away. Right?
But why do you call a rectangle a trapezoid?
because it's just another name.
It's just another name.
Classification.
Just like you're a girl and then
It's all.
Okay. Okay, so based on the fact that you're a girl, that means there's certain things that are true. Based on the fact that you're Danielle, there are more things true about you. But I'm not going to, just because you're Danielle, I'm not going to say, well, I can't use the attributes of girlness on you. Just because this particular shape is a rectangle doesn't mean that I can't use its trapezoidalness. All right? So that is a trapezoid. Oops, I meant that side to be a little bit steeper.
that is also a trapezoid
Why is it a trapezoid, Hannah?
because it has at least one pair of parallel sides and it has four sides.
It's a quadrilateral. It has four sides and has at least one pair of parallel sides. Okay, last thing I got to bring up about trapezoids. The area of a trapezoid is equal to 1/2
Height plus base 1 plus base 2.
Okay, I'm going to write it that way. So that matches what I do later on. The area of a trapezoid is 1/2 times base 1 times base 1 plus base 2 times height. All right? And by the way, base 1 and base 2 refer specifically to the parallel sides. All right? Is everyone okay with that review of trapezoids? All right? Now let's bring trapezoids into calculus. You ready? So here is my speed curve. Now I can draw rectangles and I can do them based on a right-hand estimate or a left-hand estimate or a midpoint estimate. We've already done that. What if we looked at this speed curve based on trapezoids?
That's so
Yeah, wait, why did we do this?
Because it's straight, it's not a curve.
We're not smart enough.
Oh, you can.
Well, there's a couple of things that go on here. I could, one, calculate the area of each of those trapezoids based on that trapezoidal area formula, 1/2 quantity B1 plus B2 times H. Okay? And when I do that, how do you think that this estimate would match?
Because it covers everything under the curve.
But nothing.
Pretty much.
Well, what we have to imagine, I do this as a bunch of stick lines, but you have to imagine that the speed curve or the velocity curve is actually smooth.
Oh, so it's getting closer.
But it's closer. There's a lot less area that's not being covered. It's probably a really good estimate. A really, really good estimate. All right? So the trapezoidal estimate, the TRAM, is a pretty good estimate. Because it covers more of the area underneath the curve. A couple of other observations. TRAM, in this case, TRAM 6. Oh, I love this point of this lecture. TRAM 6 is RRAM 6 plus LRAM 6 divided by 2. The trapezoidal estimate is the average between the LRAM and the RRAM. That's item number 1.
So it's like a mix.
Okay? No, it's not. It's not a midpoint. It is not a midpoint. Okay. Second point that I want to raise. All right, is that I'm going to draw something that is concave down with 3 subintervals. Stephen, are you paying attention? Because this is for you. Ready? Yes. Yes. Watch this. I'm going to estimate the area under that curve using trapezoids.
This was from what I remember.
Would you say, based on these 3 trapezoids, that I've overestimated or underestimated the area under that curve? Underestimated. So, TRAM underestimates if F is concave down. Let me draw a concave up curve with, and again, I'm making this really simple. So here and here. And do you see my 3 trapezoids now? What's my conclusion? TRAM overestimates when F is concave up. So that's what I wanted to get to. I have actually midpoint. There is no guarantees on any overestimation or underestimation. As far as I know.
It seems like there would be, though.
I agree. Okay, so what could we do to find the area under this curve? Well, since we already did the LRAM and the RRAM, we could just add them together, divide by 2, and that would give us the TRAM. If we wanted to do it by hand, we end up applying the trapezoidal area formula to each of the 6 trapezoids that got created. There's first trapezoid, second trapezoid, third trapezoid, fourth trapezoid, fifth, sixth. And when you add them all up, you get your estimator. By the way, one other thing I always think is interesting here. When we did RRAM, we essentially didn't use the first data point. When we did LRAM, we didn't use the last one, but TRAM uses them all. Remember, midpoint threw away 4/7 of them in this example? TRAM uses them all. I think so. All right. How much time do we have left?
7 minutes.
7 minutes? Okay, let's see what's left on this. Left to
It's like
the.
this homework's gonna be really hard. Just feel like it's long, just a lot of hard.
Hold on. Okay. Okay. So, I got one last piece of the puzzle for you. I mentioned that this particular notation, the limit as n approaches infinity of the sum from I equal 1 to n of f of x sub I, star times delta x. Delta x is another way of saying the interval.
Yeah, wait, should we naturally write?
You should write this down, and then we're going to write another. We're going to write down another way to write it.
Okay.
All right. This notation is stinky.
Yep.
It's poo-poo caca. Well, no, it's really good mathematics, but it's really difficult to write it down. I want a different notation to get across the same idea. All right? So here's the old stuff that we looked at, we barely knew, and now I'm going to show you the other way of saying the area under the curve f on an interval with an infinite number of intervals. And that notation is called the Leibniz notation.
Another Swiss
Wait,
name. I bet.
Oh my gosh.
Integration.
Mind blown.
Okay. So what does this notation mean? It means I'm going to find the area under the curve. What curve? The f of x curve. From A to B, that's x values. Okay, how about this? Here's the first problem that we did, what, 5 times? Right? And I wanted the area from underneath there. This area is the integral from 0 to 1 of x squared dx. We always use this dx differential placeholder to mark the end of our integral. And this statement here is the area, the curve under which we're finding the area. So I can summarize a lot of ideas in a very small space. So we call the definite integral is another way of writing the notation about area under a curve on a particular span of x values. The x is a differential. It is a placeholder that represents the width of any particular interval. You know how we feel like delta x, there's a movement in x? Well, when we did our problem this first time, our delta x was 1/4, because we were looking at intervals of 1/4. If we did it with 10 intervals, those delta x's was 1/10. If we did it with 1,000 intervals, that delta x was 1/1000. When we talk about doing an infinite number of rectangles, where each of those rectangles are infinitesimally thin, we use the notation dx to represent an infinitesimally thin slice
So
of
if there are
x.
10 rectangles, the x would be 1/10.
Well, when they're that thick,
You know.
we use delta x.
Okay.
When they're this thin, we use dx. And it represents the same idea, the width of a rectangle. You'll note that x squared then represents the height of the rectangle. And this elongated s, if you want to, put it in your mind as representing to add up the summation of all of those rectangles. Okay, you seem to be putting your books away. I still have 3 minutes. All right? Now I just have to figure out what's the next thing I'm going to say. Okay? I think you guys should start just talking over me, because that's the best way to get this really hard information down. Darn it! I made a resolution to stop being so sarcastic.
So did I, but it really failed.
All right, so again, in the two notations, we have placeholders for the function. We have placeholders for the slices of x that represent the width of an individual rectangle. All right? And the elongated s, like the sigma notation, represent to add up. All right? We're not doing that one. The elongated s, you can think of as to add up a bunch of the rectangles that make up that space. All right? And I'm not doing that one either. I'm not doing that one either. I'm not doing that one either. Nope, not doing that one either. Oh, here's my last point that I have to make. Notice the word negative areas is in quotes. I have to get this point in. All right? Our delta x and our dx are always considered to be positive values as we go from left to right. But we know that sometimes our functional values are negative. So sometimes we're multiplying a positive dx or delta x value times a negative function value, and when we get those values in our summation, those are negative, and they have a negative effect on our adding. All right? Delta x and dx are considered positive values. All right? Here's what I need. All right? I need you to, and this is going to be really weird. Oh man, I need you to go to my website this afternoon to find out what your homework is.
All right.
That's what we'll do.
We don't have
Or-
to do it.
Then you can call me.
I don't have it.
Then I'll call. Then I will
Numbers on this website.
Pony Express the message to your house.
No, please.